In Lab 1, we discussed constant velocity motion. The purpose behind this lab was to construct a model of the motion of an object that is moving at constant velocity. We were to film an object moving at constant velocity and then use Tracker to analyze the video and extract its position and corresponding time. Then, we were to use VPython to create a theoretical model using the same conditions as our video in order to see how accurate our experiment was. The main concept that this lab was used to illustrate was Newton's second law, or equivalently, the momentum principle. In its simplest terms, Newton's second law states that in order for an object to accelerate in any direction, there must be a net force acting on it. If we were to explain this in terms of momentum, we would say that if there was a change in momentum, there is a net force acting on the system. If we write out these as a formula, we can use the formulas for velocity and position update in order to show Newton's second law. The velocity update formula states that the final velocity of an object is equal to its initial velocity plus the net force acting on it divided by its time, divided by its mass, multiplied by the change of time. The position update formula states that the final position of an object is equal to its initial position plus its average velocity times its change in time. For the purpose of our lab, the net force acting upon our object is zero, which means that there will be no acceleration and no change in momentum of that object. Therefore, the average velocity is equal to its final and initial velocity. When we open our video in Tracker, we see that we've specified that the origin is at the center of the ball and that the ball moving to the right is in the positive x direction. When we play the video, Tracker collects the position versus time data moving in the positive x direction. Before we open our code, we have to make some calculations. First, we have to specify the initial position of our ball, which came from our Tracker data. The initial velocity of the ball was calculated by taking the distance of the ball traveled from t equals 0 to t equals 0.033 seconds, and then dividing that by 0.033 seconds, which gives us our initial velocity. Since we know that the velocity of the ball will stay constant, we know that this initial velocity will be the velocity of the ball throughout the experiment. When we look at our code, we see a couple things that we had to change. First, the ball's mass had to be changed to the general convention for the mass of basketball, which is about 0.59 kilograms. We also had to input our initial position using our Tracker data, as well as our initial velocity, which we calculated in the slideshow itself. We also had to stop the code at t is less than 1.2 seconds, as that was the time for the amount of frames we chose to study. We also had to change our fnet vector to 0, since if the velocity doesn't change throughout the experiment, the fnet acting on it must be 0. We can see this in our velocity update equation, where it states that the final velocity of the ball is equal to its initial velocity plus fnet divided by its mass times delta t. Since fnet is 0, the final velocity of the ball will be equal to the initial velocity of the ball. When we do the position update, we see that the final position of the ball is equal to its initial position plus its velocity times delta t. If we were to run this program, we see this illustrated as the position of the ball increases as the time increases, while the velocity stays constant. When we compare our experimental and model data, we see that they are very similar, except our model data is just a little bit, our experimental data is just a little bit lower than our model data. This may be because of a huge assumption that we made in our experiment, that all the net forces acting on the ball equaled 0. Even though we assumed this in the experiment, the lack of control that we had over our surroundings meant that there could have been any number of forces acting on the ball that we didn't know about, including friction from the floor or air resistance. This likely accounts for the small variation between our model data and our experimental data. When I filmed the experiment and set the axis, I set the positive x direction as moving to the right, so when the data was plotted, the data moved in the positive y direction with the positive slope. If we were to flip this axis, meaning that the ball moving to the right was now the negative x direction, the graph would move in the negative y direction instead. We can see this with this graph. Basically, this represents the initial data of the ball, while this data represents if the ball moving to the right was now the negative x direction. We see this as basically just a reflection over the x-axis, as the ball still moves the same displacement, it's just in a different direction. What does this mean? When we set the net force equal to 0 in our computational model, our results were very similar to our experimental ones. However, it is impossible for us to know just how many forces were added together for us to get a final net force of 0. There are thousands of net forces in the universe, so we have absolutely no idea just how many of them combined to give us that net force of 0.